Hey there, welcome to Pomodoro Joe for Wednesday, November 8th, 2023. Today we're doing LeetCode problem 2849. Determine if a cell is reachable at a given time. This is a medium problem. So we're given four integers, sx, sy, fx, and fy. So that's the starting x, starting y, finishing x, and finishing y coordinates, and a non-negative integer t. In an infinite 2D grid, you start at the cell sx, sy. Each second, you must move to any of the adjacent cells. Return true if you can reach the cell fx, fy after exactly t seconds, or false otherwise. A cell's adjacent cell are the 8 cells around it that share at least one corner with it. You can visit the same cell several times. Okay, so to summarize, in this problem, we're given an infinite grid and we're given two coordinates, a starting x and y coordinate and a finishing x and y coordinate. And we're also given this variable t, time. So we're going to start at the starting coordinate and we need to end at the finish coordinate, and we have to move one step or one cell for every second. And on each move, we're allowed to move in any of the adjacent 8 squares. So if we're here at start, we can move to this one, this one, this one, this one, so on and so forth. So we have 8 squares around us that we can move to. All right, let's see, we have a couple examples. Okay, so this seems pretty straightforward. I think the initial thought would be, let's just do a graph traversal where we actually start at the start coordinate. Then for every tick of the clock, for every t, we can traverse to one of these 8 squares, and then we recurse. From that square, we can do the same, and then from the next square, we do the same. For every tick of our clock, we just look at our 8 adjacent squares. So that's sort of the brute force approach, but I think we can do a lot better. If we take a look at our grid here, we can see that to get from start to finish, we can go straight across and then straight down, and then straight across, or something in between. All right, so let's put 25 minutes on our Pomodoro timer and we will get started. Okay, so the first thing to notice here is we are constrained to this grid. Now, in order for us to get from our start cell to our finish cell, we have to traverse at least this number of spaces in the x direction. So that number of spaces is the difference between our start x and our finish x, or the finish x and the start x. It's the absolute value of the difference between our dx, or our sx, and our fx. And we also have to traverse a certain number of squares in the y direction. And again, that's just the delta between our finish and our start in the y direction. Now we could traverse all the x's first and then all the y's, or all the y's first and then all the x's, or we could do a little bit in between where we take a step in both the x and y directions at the same time. But we'll have to do at least this number of steps in the y direction and this number of steps in the x direction. Of course, we can do 2 at the same time, but the point is we have to do at least that many. So let's find the difference in our x's and our y's. So our delta x, that's going to be the difference in our x, and that's the absolute value of the difference. That's it's not dx, it's sx. Actually, I'm just going to call this dx. So this is our delta x. So that's going to be the absolute value of our start x minus our finish x, or our finish x minus our start x. So I'll do finish minus start. And what's our dy? Well, it's basically the same thing, but for the y value. So absolute value of our finish y minus our start y. Okay, now we know how many steps we have to take in the x direction and the y direction. Now we could take steps simultaneously in both the x and y directions. So what's the max number of steps we'll have to take? Well, that's going to be the max of our dx or dy. So we'll call this max steps, or I'll just call it steps. Cool. Now, since we're allowed to take 1 step per second or per unit of time, as long as our time is greater than the number of steps, or greater than or equal to the number of steps that we have to take, then we can definitely reach this square. So we can just return steps less than or equal to time. Great. So that should do it. Let's run this and see how we do. Okay, seems to work. Let's submit this. And we get a wrong answer. So let's take a look at this test case. So this test case, we start at 1, 2, and we have to end at 1, 2. Okay, so we start and end in the same position, and our time is 1. And now it says here we must move on every step or every unit of time. So we start and end on the same position, but we have to take at least one step because there's 1 unit of time. So in this case, we actually have to leave our ending or our finished position, and we can't get back to it because we only get 1 step, and so we'll fail. So this is kind of a unique edge case. So we can just have some special case code here for that. So let's just do this. So after we calculate the steps, we can just check if t is equal to 1. So this means we only get 1 step. So we'll have to return false if steps is anything except 1. So if steps is also 1 step, that means we know our finish is 1 step away from our start, and we can definitely reach that in 1 unit of time. If it's not 1 step, well then we'll fail. So we have to check here. If t is equal to 1, then we can return steps is equal to 1. If steps is equal to 1, we can take the 1 step and we pass. If steps is anything but 1, then we have to return false. So let's try this. All right, that works. Let's submit that, see how we do. All right, and we pass. We don't do great though. Let's see, we only do about 47% for runtime. We do good in memory though, 94% in memory. Okay, so it's probably these absolute values and this max calculation, so we can jump back and do a little bit of work. Let's see. Steps will be dx. If dx is greater than dy, else dy. So this is just our own version of the max calculation. Let's see, we can also do, well, actually I'm going to leave it like this. This is fine. Let's see how this goes. Actually does worse. Now we're down to 27% for runtime, 73% for memory. That surprises me. All right, we can do a couple things here. We can do this. All right, so that gets us up to a 56% for runtime and a 94% for memory, so that's pretty good. It'd be nice if we could do better, but let's see what the top one does. Oh, so this one has a nice early out. Oh, so this is interesting. I kind of thought that this, like the absolute values, were going to be the thing that was taking all the time. But this top scoring solution also uses the absolute values. That's interesting. I wonder if it's having this return early. We could try that. All right, let's give that a try. Let's just see. All right, now we're at a 70% for runtime, 73% for memory, a little bit better. Well, I think that's it for me tonight. Yeah, I think that's it for me. So for this one, we started out with a potential grid traversal type problem, but just by looking at it logically, using a little bit of math, we were able to solve this much faster with a little bit of code, a little bit of math, a little bit of logic. All right, well, I hope you enjoyed this. Hope you had fun. Hope you learned something. Hope you can go out and write better code.